Welcome, everybody, to this joint webinar today between Luceda Photonics and Spark Photonics. We're going to be talking about thin film lithium niobate, or TFLN, for photonic integrated circuits, or PICs. My name is Kevin McCumber. I'm the CEO and co-founder of Spark Photonics. Spark Photonics is a PIC design services and software company based in the United States, and we are the North American representative for Luceda Photonics, a PIC design and layout software company based in Belgium. With me today are Drs. Sean Nealon and Matthew Delaney. Sean is a photonics engineering lead at Spark Photonics, and Matt is business development manager for North America at Luceda. Just to quickly go over our schedule, I'll be turning it over in a moment to Sean, who will discuss why thin film lithium niobate is relevant to PICs today, as well as some applications and innovations we're seeing in TFLN for PICs. Sean will then hand it over to Matt to show us some design and simulation of TFLN PICs, including a demonstration of a simulation in TFLN using Luceda's IPKISS software that I think you'll find very interesting. And then we'll wrap up the prepared portion of today's program with Sean discussing avenues towards fabrication and packaging of TFLN PICs. And this is an area that we're seeing a lot of excitement in today, and a lot of growth. We've left ample time for Q&A at the end. In that vein, we ask that you please put your questions in the chat if you'd like to ask them right away. Ask that you note the speaker and the slide number so that we can reference them when we get to your question. We plan to address questions during the Q&A session at the end. You can also ask your question live then during the Q&A session at the end. And yes, this meeting is being recorded, and the recording will be distributed afterwards, sent to you via email about 2 business days after this event. All right, it's now my pleasure to introduce Dr. Sean Nealon. Sean is the photonics engineering lead here at Spark Photonics. He has a doctorate from the University of Delaware, where his thesis concerned high-speed modulators in TFLN. Sean is our resident expert in TFLN, but also gets his hands into a lot of other material platforms and a wide array of applications. So I'm sure he'll have a lot of interesting things to share with us today. Sean, the floor and the attention of everybody here goes to you.
Thanks, Kevin. Let me see if I can share my screen here. There we go. All right, thanks again, Kevin. And to everyone in the chat, again, this is going to be a wealth of information, so please put all of your questions in the chat, and we will try to get to all of them at the end of it. Quick overview of Spark Photonics. So as Kevin mentioned, we do design and consulting services. Now, this is more or less everything PIC related in almost all of the material systems that you can think of. We go from design and layout, PDK development, consulting, so we can help anyone that needs any sort of simulation work, layout work, or tape out. Kevin also mentioned we do some software and hardware, so we are the North American distribution and support partners for Luceda, where Matt will be talking about IPKISS just a bit later in this talk. We also have some education and outreach programs, and if you're interested in that, please reach out. So Kevin mentioned lithium niobate is very near and dear to me. I did my doctorate in high-speed modulators, and in the industry, we see a lot of lithium niobate coming into play in quantum photonics, high-speed modulators for telecom and datacom. And so I wanted to quickly introduce why we're using lithium niobate here and why we're talking about it, and maybe a bit about how it compares to other photonic materials. So, lithium niobate is not the only photonic material, but it is the one that we'll be focusing on today. To quickly cover some of the other ones, on the left here, I've tried to outline some of the materials that you'd think of as active materials. Now, these are things that you could make a laser out of, you can make photodetectors out of, or even high-power electronics and transistors outside of the photonic world. So this is indium phosphide, gallium arsenide, indium gallium arsenide, and these are all, again, very common materials that we see for active components. On the right side, aside from thin film lithium niobate, we also have silicon and silicon nitride. Now, silicon is perhaps the most ubiquitous material. Really great for high density. It's very cost effective and scalable. Silicon nitride, another great material, supports very low loss applications. Great for sensors and quantum photonics, but it doesn't have any active properties like thin film lithium niobate. So thin film lithium niobate has then become more prevalent in industry for things like high-speed modulators, frequency combs, nonlinear optics, which we'll of course go into a bit here, and quantum photonics. So what are the material properties of lithium niobate that make it so interesting to us? First and foremost, low optical loss. None of us want our light to go away on our PIC. So lithium niobate is nearly transparent from wavelengths of 300 to 5,000 nanometers, or 0.3 microns to 5 microns. And that is a huge range when we think about photonic materials that generally only see a transparency window of maybe 500 to 1,000 nanometers. So this material can be used across a wide variety of applications. High-speed modulation, we'll talk about this in just a bit, but lithium niobate uses a modulation scheme that's different from silicon plasma dispersion or indium phosphide or 3,5-based modulation. So this promotes high-speed operation and low-power operation. Now, a big requirement in quantum photonics as of late has been high power handling. Lithium niobate can support extremely high power density in its waveguides without any sort of third-order effects or crystal damage that might blow up your chip. So what is a history of lithium niobate, and how did we arrive where we are today? It actually goes back pretty far. 1949 was the first synthesis in a lab of lithium niobate as a crystal. At that time, they didn't know that it would become a great photonic material for thin film devices. This is purely the first breakthrough and where we made lithium niobate. It actually took until about the 70s to become used in modulation at all. And at this point, they started to diffuse titanium into the lithium niobate to form waveguides. So we'll talk about this more in just a second, but this was really the start of lithium niobate for modulation. And this is what we would call bulk lithium niobate. After that, you want to make your devices smaller, faster. And with the onset of the smart cut process, which I'll cover again in just a second here, we were able to make thin films of lithium niobate. So what do I mean by thin films? Generally, the bulk lithium niobate films are on the order of 500 microns to 1,000 microns thick, whereas these thin films of lithium niobate are on the order of 100 nanometers to 1,000 nanometers thick. But this was still a very difficult process to achieve. So 2013, we really started to see these commercial wafers coming into play where you could buy a thin film of lithium niobate on a wafer that you could use. Soon after that, foundries started using them. So now we see the emergence of TFLN in the commercial foundries. So now you can order a wafer with devices on it with a PDK component set to implement in your system. A bit then on how bulk lithium niobate compares to thin film lithium niobate and why thin film lithium niobate is so special. Bulk lithium niobate, of course, used since the 70s, is a great medium for high-speed modulators. Bulk lithium niobate modulators operate up to 300 gigahertz, and this is a great sort of system to achieve high-speed operations for telecom and datacom applications. But a bulk lithium niobate waveguide and a bulk lithium niobate modulator is pretty big. These are on the order of 5 to 10 centimeters long. And if you think of a photonic chip, you're operating on the order of 10 millimeters. So we can't fit these on a photonic chip with other components. These are generally coupled to fibers on each side and implemented in perhaps a free space optic system. So how do we bring the beauty of lithium niobate into a PIC? Well, we create these thin films of it. On the right here is a thin film lithium niobate waveguide cross section. At the heart of it, the thin film lithium niobate layer is bonded to a silicon wafer with a molecular bond, and I'll go over that again in the next slide. But this creates the ability, or gives us the ability, to densely integrate these devices onto a chip. Our waveguides are smaller, tighter bending radii, so we can make PICs out of this, and we can incorporate other components. So what is the smart cut process then, and how is thin film lithium niobate made? The core of it is, the first steps here is we start actually with a bulk lithium niobate wafer. This is again, that 500 micron to 1,000 micron thick wafer, and we implant helium ions into it at a certain depth. These helium ions then create what's called a damaged layer in the lithium niobate, such that when we molecularly bond that lithium niobate on the top right to a silicon wafer, we can actually crack off the top of that film. And it cracks off at that damaged layer, leaving that thin film of lithium niobate behind. This is still a bit rough, so in the final step, we want to perform some wafer polishing on it to make it a smooth layer, such that when we etch our waveguides, we don't have additional scattering losses. So then, now we know what lithium niobate is and how it's made, and that it can be created in a thin film. But what are some actual applications of this? Here I've highlighted a few of them. This is not an all-inclusive list, but it's perhaps the most common applications. We go from high-speed modulators to frequency combs. Quantum photonics is a huge one, acousto-optics, and LiDAR systems. In the next few slides here, I'd like to focus on the use of high-speed modulators, which in some cases are really the core of optical systems that we'll be talking about here. This essentially enables these next generation networking systems in telecom, datacom, and even quantum photonics, where we need high power operation, which I touched on a bit previously. So why do we need these high-speed modulators, and why can't we rely on what we have now, silicon photonics or indium phosphide, to do the job? Lately, we've seen a big spike in networking needs from AI. I'm sure we've all tried it out. Cloud computing, virtual reality, even 5G. More people are getting smartphones and using things like the Internet of Things. So legacy devices then, as I have in the bottom left, which we could think of as, again, those silicon modulators or those indium phosphide chips, these are sort of frequency limited and power limited. When we think of silicon modulators, maybe it's possible to achieve 50 gigahertz operation, but it's at quite a cost, high loss, and power requirements are much higher. Now with the onset of TFLN, or thin layers of lithium niobate, which we could put on a silicon photonic chip or order devices from a foundry, we can achieve very high speed modulation up to, in some cases, a terahertz, but more commonly for these sorts of systems, 100 gigahertz, 200 gigahertz, to enable what I would call the networking needs of the future. High-speed operation for chips that replace existing chips in telecom and datacom centers, in other words. So then what is a modulator? I would call it the core of TFLN multifunction systems. This is a great image that kind of shows all of the different components that you can make on TFLN, and I'll leave it up for a bit here so you guys can take it all in. But I'd like to highlight, let me see if I can set my mouse up here. Hopefully everyone can see this. Some of the evolution or the, from zero complexity or low complexity to high complexity TFLN devices. In this talk, I'd like to highlight the phase modulator in the bottom left as the basis for these things. So the phase modulator is purely modulating phase of a waveguide. So that is the wave of light you can advance or slow down the speed of that. Now, we can form an intensity modulator out of this, which instead of just speeding up or slowing down your speed, you're now creating a 1 or a 0. You're turning on or off your light. We can do this with what's called an intensity modulator. I'd then like to highlight the IQ modulator, or the in-phase and quadrature modulator. This is something that allows us to create much higher data rates on chip. So what does modulator look like? This is a fabricated TFLN chip. The modulator outlined in this dotted line is shown here with some zoomed in views of various components. Common on TFLN chips for things like this is a 2x2 MMI splitter combiner, a 1x2 splitter combiner. You could even use a Y splitter, a directional coupler, if you're familiar with that. We have thermal optic tuning electrodes, which heat up or cool down your waveguide to adjust the phase in sort of a steady state way, so you don't have to use your high-speed electrodes for that. And then, of course, at the core of it, we have our high-speed electrode design. TFLN is a great RF material. It allows you to do very high-speed switching with low RF loss. So how does that actually work then? And when I talk about a modulator, why is it so important? Here I've highlighted some of the core characteristics of a modulator. And first, I'd like to highlight the fact that a modulator converts an arbitrary electrical data signal and overlays that onto, in this case, an amplitude modulated optical signal. More on this in a bit, but the way that it does this is when we have our optical field highlighted in the center here, going through our waveguide between our metal electrodes, in some cases gold, copper, aluminum. The fact that there is an electrical field present across the lithium niobate material slows down or speeds up the light in that material. So it adjusts the optical index. And by doing that, we can speed up one arm of our device and slow down the other arm. And then when our light gets to this combiner at the end, it will either be constructive or destructive interference, and we get our modulation pattern. So imagine you're at your computer and you want to send a message to your friend somewhere else over a fiber optic cable. You need to convert that electrical message or signal to an optical signal to send over that cable such that your friend can receive your message. And that's the beauty of TFLN, and we can do that very quickly with this material. It's likely that the message to your friend will go through something like this: an IQ modulator, in some cases dual polarization IQ, essentially a scheme of intensity modulators that allows us to send information more quickly than using a single modulator by itself. On the right, I've highlighted some of the encoding formats that you could use. The zeros and ones here correspond to bit sequences, which your friend at the end of the line could interpret as data. And down here, tried to highlight the increasing networking needs of the future that is pushing us towards this material. Finally, I'd like to just touch on some of the what I call hybrid integrations or hybrid platforms that we can achieve using thin film lithium niobate. On the left here is what I would call monolithic thin film lithium niobate, or a single material for our waveguide. That single material, of course, lithium niobate. This is the best for voltage bandwidth performance, meaning as we increase our voltage, generally we will decrease or increase our bandwidth. So it's sort of an inverse relationship where generally we want as low as voltage as possible and as high as of bandwidth. By monolithically integrating your TFLN waveguides, you have all of your field or most of it in the TFLN material where you want it. and you can get the best performance. Now, it can be difficult to etch TFLN. So in a lot of cases, we integrate silicon nitride or silicon on top of that TFLN layer, such that we only have to etch the silicon nitride or silicon, which a lot of foundries are more set up to do. The downside of this is that you then have some of your optical field in the silicon nitride or silicon, which can be maybe lossy or at least pulls power out of the TFLN, which is the material doing the modulation. It has benefits, but it has downsides. So with that, I'd like to hand it over to Matt, who will give you a bit of a demonstration on how to design in TFLN and what we can do to perform simulations on our TFLN chips.
Great. Thanks, Sean. Just checking, is everyone able to see my slides here? Yep. Thumbs up from Kevin. Thanks. All right, let me quickly introduce Luceda. We're a Belgian company founded about 14 years ago. Although, as you can see here, we have partners or offices all around the world. So we have quite a global presence. Our sort of role as a company is to try and help designers achieve the first time right experience that we see in electronic IC design. And I'm going to touch on that and then try and illustrate that a little bit with some examples from our Luceda Academy. What we mean by this is it's quite common when designing electronics that you can lay out a design, run some simulations, look at the yield, send it off to the fab and be completely confident that it's going to work and that your simulations are going to match and it's going to be valid. And that cuts down the design cycle and it cuts down the cost. I think anyone in the chat that's familiar with integrated photonics was going to know that that's not the state of play that we have yet. We're still a maturing industry, and we're still finding out the hard way some of the hurdles. But we believe that through software we can achieve something that's pretty close to that. And there's kind of four things that we think are particularly valuable to this. The first is obviously reducing design errors, both through the design of the software and the way you use it. We think we can minimize those errors and hopefully reduce the number of iterations it takes to get to a product that works. We also leverage a standard language, which is Python. It's sort of becoming the language of science, I think, in a lot of ways, and it's fairly commonly used. So not only is it easy to hire people or to train people, but also it's easy to interface between tools because we have this common language. Then obviously in the bottom row, I've kind of put here design manufacturable PICs and improve time to market. Really, that's what it's about. Our customers, they're making PICs, they're selling products, and we're trying to do this. We work with academia and with research institutes, but the core of this is going to be looking forward to products that you can buy. We partner with a lot of people. This is just our design kit, so it's PDKs, ADKs, TDKs. So that's design kits. On the left, I've put some of the people we partner with, and I'm going to go a little bit more in depth into the lithium niobate offerings. In the middle is kind of this code-driven flow that I'm going to come back to shortly. And on the right, we can see the different products that we have. So we have the Luceda IPKISS platform, which is what everything builds on and what I'm going to be using today. Then we also have products for specifically designing and simulating AWGs, and one for managing and testing of IP. We also have links with commercial partners, so we don't do fundamental simulation ourselves. We don't have an FDTD engine. For that, we have links with ANSYS, with 3DS, with Tidy3D, etc. As I mentioned, these are some of the TFLN foundries from around the world. It's not exhaustive, but I think it's just a highlight of some of the key ones. If you're interested in any of these or their PDKs, reach out to them or reach out to us. We're always open to having a conversation. You'll also find an up-to-date list of all the PDKs we support, as well as their contents and things like that on our website. So that's also a great resource. As you can see, there's some established names that I'm sure everyone knows, but there's also a lot of new players on the scene. TFLN is really an up-and-coming material, and I think that's evidenced by the sort of the number of foundries that are appearing year on year, it feels like. There's also packaging facilities where you can go and have these things put in a box and made and tested. But I'll leave that for Sean to come back to later. So what is this design cycle that I mentioned? Well, really, it's kind of the heart of your flow. If you're a photonics company, this should be your bread and butter. Usually it starts either with component design or with just using components from the PDK. But in any case, you would want to run some simulations to validate the designs. This is not only to validate the designs, but it's also to build sort of compact models and generate some data sets for them. As I mentioned at the start, we don't do this directly. We're not trying to compete with ANSYS or Tidy3D. We have links with them. And what that looks like is that you can do a layout of a component in IPKISS, or you can import a component from a PDK. You can write a quick simulation recipe, click run, and it will push all of that. It will push the layout, it will push the data from the PDK, the material stack, push that into an engine, run the simulations, and then return the results back into IPKISS. Let me actually turn my pointer on. Um, Once you've kind of got your components and you've built the models for them, then you move up a level to circuit design. So this is where we're putting our components together just like Lego bricks to achieve something functional. The IQ modulator that Sean showed earlier is a nice example. And this is where it no longer becomes feasible to run sort of full chip simulations using an FDTD or an EME engine. Our approach for that is we use a transfer matrix solver, which we'll see later. But basically, we think this is where a lot of the work needs to go into sort of optimizing the design, working on the yields, looking at the, if your correlation between certain components is impacting performance or not. Once you've settled on a design, you've run your simulations, you're happy with it, then it becomes a question of validating it. So there's kind of functional verification as well as physical. Does it pass the Foundry rules? Yes, but more than that, is it actually going to work? We also have some things that might be useful here. We have a link with Checkmate, which can be used for running DRC, and we also have IP Manager, which is used for running regression tests of libraries and PDKs and keeping your design flow in check. Right. When it comes to Tiflon specifically, there are a few things that you need to consider. Doing the layout, putting the shapes in layers is pretty similar to any other material. It's just these are the things you have to think about in the back of your mind. And it's all to do with the fact that the orientation is important for a material like this. The problem is that, particularly for waveguides, but any component, even if they have the same shape, they'll behave differently depending on their angle. And what this can impact is things like when you have components, you can't rotate them easily and still know their performance. But also if you're building smaller circuits and then nesting that into a hierarchical design, which you have to as circuits become more complicated, you need to keep track of the transformations you've applied, and actually that it can be quite complicated to work out where you stand at the end of the day. And then, of course, I put at the bottom here, finally, waveguides use both axes. If you have a waveguide that's got bends in it, it's always going to be experiencing different material properties depending on its angle. Fortunately, there's an easy solution for all of this, and that's something that we're passionate about, which is layout-aware simulation. We don't build a layout and then separately run some simulations and hope that the two things are in step. We directly run the layouts based on the simulation. Sorry, we base the simulations directly on the layouts that have been created. There's no like user mapping between them or anything like that. It's a direct one-to-one. And doing this means that we can avoid a lot of the complexity that otherwise would arise. It's also easy to do. I'm going to show it a bit later, but this is the plot, or this is the code to run the simulations for the results I have in a few slides' time. So it's not much. How do we approach this? Because we still have to deal with this complexity at a software level. The first thing we want to do is we try and lock the orientations of components. So in all of our Tiflon PDKs, components are validated in a horizontal or vertical configuration, and then they are not allowed to be rotated. Even if you put them inside a hierarchy and try and rotate that, it will not let you. And that's because the Foundry has specified that it shouldn't be. It should work in one way. On top of that, the waveguides, we split them into pieces. We actually look at every point pair between them. And for each section, we calculate the length and the angle of that section. And then finally, we can pass that into some equations and work out the group index and effective index, and use that in the simulations that we run at a circuit level to calculate the overall response for the waveguide. If anyone's interested, it looks a little bit like this. We might have a waveguide. I've split this up into 5 sections, but really it would be hundreds. And these can all be considered independently. We can look at them. We can calculate the total phase, the waveguide loss, the total delay. We can calculate all of these things using the properties inside the PDK for the material, depending on its orientation. To give a real world example, this is one I quite like because these two designs, functionally they're the same. If you look at them, they have the same path difference between the upper arm and the lower arm. It's just a question of how much of that difference is in which orientation, how much of it is vertical and how much of it is horizontal. And I'm just going to step out from the slides because I'd actually prefer to do this as a demo. So if I come across here, I'm just going to run some code. These are the layouts up here. It's going to run through them. This is the first with a long horizontal stretch. And then the second layout is the same thing with a long vertical stretch. And in both cases, what it's going to do is it's just going to run the simulation, which is what I see here. And it's looking at the differences, or it's plotting the difference between these two MZIs based on the birefringent properties of the TFLN. And actually, if I zoom in around 1550, we see there's not a lot of difference. But if I come out to the wings, we see there's quite a dramatic difference. Obviously, this is the response. So if you look at this on a log scale, you could see a massive power shift even over a couple of channels. In this case, it's quite obvious that these two designs are different. So these are them in a GDS file. But if I make that difference more subtle, it actually becomes very hard to kind of see that by eye or even by any other sort of checks. What I've done here is I'm going to run the same simulations for the same layout, but instead of having a longer path difference, in this case, I've got a 40 micron path difference between the top and the bottom. When I close this, it's going to plot the one with a vertical configuration, which functionally looks the same. And now it's running the simulation. And what we're going to see is that actually for a smaller offset, we see quite a dramatic shift across the entire C-band range. What this means is when you're doing your layouts, doing your designs, you need to start thinking about how to optimize the space you have available to achieve whatever it is you need. In this case, maybe it's preferential to use the vertical over the horizontal, or maybe you just need to think about different parts of your circuit and make sure that they have the same properties. I'll come back to here. As Sean pointed out earlier, we have the nice application example of an IQ modulator. We have this on our website, which is where I'm drawing these things from, so please go and check that out later. But an example layout would look something like this. In this case, we're using our own PDK called SciFab. It's not a real PDK, but it's complete. And then we're getting this packaged through Fix. This is the layout. You can see we've got let me show my pointer again. You can see we've got the two sets of MZIs here and here, and then we've just got some basic MMI splitters and routing it back to a fiber array on the left, sorry. This is a schematic that shows the circuit. What we can do is we can write this up in code and generate our layout. And then at the same time, once we've got the layout generated, we can start running some simulations. If you're interested in sort of getting more into the layout, I don't want this to become a coding lesson, but we have some sessions coming up. The next one, I think, is on the 27th of March. So feel free to subscribe to them. That's just a very basic introduction into how we kind of generate layouts and things like that. We also can run simulations for eye diagrams and for the different modulation formats that Sean mentioned earlier. Again, I don't want to get into these in too much detail. I think it's maybe beyond the scope of just a TFLN talk, but we can see that for BPSK modulation format, this is the performance of the modulator that we designed. We also see a constellation diagram. This is quite a simple modulation format, or you can move to something that's a little bit more complicated, something like this, where actually it becomes a little bit harder to work out what's going on. But again, from the software, we can extract different parameters of the system, such as the error rate and the crosstalk. Something I did just want to highlight, if I come back into the code, all of this is very easy for the user. If you've already generated the layouts and the data is available for the PDKs, in this case, I've just used some synthesized data to make sure there's no IP exposed. But this is really all of the code it takes to run the simulations for the two different circuits I've been showing earlier. I think having this be so easy, it becomes a very powerful tool when designing in TFLN. You can very quickly tweak things and see how it affects your overall circuit performance without having to go back to the drawing board and start designing a new component or something like that. I think that's the end of where I have, so I'll pass back over to Sean to take us through the last 5 minutes with some what is it you're talking about? You're talking about the packaging, I believe.
Let's figure out how to make TFLN devices.
There we go. Your specialty, not mine.
Well, I'll do my best. Um, so, we have now all of our TFLN knowledge. How do we use this knowledge to make a device? I saw peeked at the chat, saw some questions about packaging and production and limitations and whatnot for a real device. So hopefully I can touch on that in just a few minutes here. The biggest consideration that we have to make when we design a PIC is how will we package this device? And what exactly is photonic packaging then? Photonic packaging at its core, what I would say is the connection of optical and electrical signals to your PIC, getting data on and off of the PIC. Now, imagine you create the world's best TFLN PIC, but there's no way to connect to it, or it's unfeasible to create a wire bond or a bump pad on it, or connect a fiber. It wouldn't be the world's best PIC anymore if that was the case. So we have to think about how to, at the forefront of our design, how to start the design with packaging in mind. Of course, this is not an all-inclusive slide, but it's showing what we need to consider. On the left, the consideration for fiber coupling. Will fibers come out of one side of the PIC, both sides? You could use a grating coupler, an edge coupler. There's many options for this. Electrical connections then, to the right of that. This picture shows wire bonds to the PIC. In this case, the designers have created it such that there's no crossing over of wire bonds. They're all separated from each other to minimize crosstalk. Another option for RF and DC electrical connections to a PIC would be bump bonding or flip chip bonding. This is a great option for dense integration to avoid high-frequency CPWs or microstrip lines routing all over the PIC and imparting crosstalk on each other. Or additional noise or heat. So on the right of that, once we've successfully designed our PIC to be packaged, I wanted to just show a quick example of what a packaged PIC might look like. I've highlighted in this case, the fixed characterization package, but this is one example of many different ways to package a PIC. In some cases, PICs are hermetically sealed, such that there's no outside environment coming into the PIC. And in that case, we've even seen them survive space. I also wanted to speak a bit about how to actually interact with a foundry and put your devices on a chip. So generally, there's two options here. The MPW, which we call the multi-project wafer, and then the dedicated wafer. The multi-project wafer is a low-cost option generally used in things like prototyping, where you share a small space on the wafer amongst other customers. The downsides here are, of course, you have a smaller space on the wafer. You are locked into the process that the foundry outlines for you or provides. So there's no modification of the process. And you have set tape-out timelines. Generally, these are every few months. In some cases, foundries present this every few weeks, but you are locked into some timeline that the foundry outlines. A dedicated wafer, on the other hand, provides more leeway into adjusting the actual process. Maybe you want to make a metal layer thicker or adjust some waveguide width, something like that. But it comes at a much higher cost because now you're getting an entire wafer to yourself rather than splitting the cost of that wafer with other customers. But the other advantage is that generally the tape-out timelines for this are very flexible. You can tell the foundry, hey, I'd like to do a tape-out in 2 weeks on a dedicated wafer or 6 months, and they'll say, great, submit your design, and you're good to go. So Matt touched a bit on this. I'd just like to put this slide up again, to let everyone read over the foundries that now exist for TFLN fabrication. These exist across the globe, and there's more every year. We've highlighted some in China, some in Europe, and some in the USA. These foundries all have different capabilities. I touched on hybrid integration. Some of these foundries are pure TFLN or monolithic. Some allow you to have silicon integrated with TFLN. Some allow you to have silicon nitride integrated. I saw a question in the chat about photodetector integration on a TFLN chip, and I would implore you to contact us about that because some of these foundries are doing that. And then a bit on packaging facilities. These are all some of the packaging facilities that exist in the world to package a TFLN PIC or any PIC. This is not an all-inclusive list, but it's some of the facilities that I'd like to highlight here. With that, I will hand it back over to Kevin for some final remarks and to take any questions.
Great. Thank you, Sean. So a lot of good questions in the chat. Thank you all. We'll take a couple of those for our presenters, and then we'll see if there's anybody who would like to ask a question live. So if you have a question that you've been holding, please just hold it for another few minutes here, and then we'll get to it. Sean, I'll ask you a couple questions to begin with.
Mm-hmm.
First one we had was on slide 6. Regarding high power handling in TFLN, what about the photorefractive effect? This is not considered a fundamental problem. Like the question is this not considered a fundamental problem to high power operation? Curious on your opinion on how to counteract this effect in PIC products.
Yeah, that's a great question, and I certainly have a lot to say about that. I'll try to keep it short here, but I will say feel free to reach out if you have an additional question or want to chat about it afterwards. So TFLN does present a very high power handling capability, and this is important in quantum applications where you might be doing something like atomic trapping, and it takes a lot of power to trap an atom. So this is usually seen in the 700 to 900 nanometer regime wavelength, but TFLN actually starts showing a somewhat problematic photorefractive effect down in the 500 to 600 nanometer range, but it's not gone at even 1,000 nanometers. So there are things we can do then to mitigate that, and for maybe the crowd, the problem is that if you put too much power in a TFLN chip at say 500 nanometers, it will blow up. So what can we do to make that not happen? A lot of people are, and in some cases commercial foundries now, are magnesium oxide doping their TFLN. Essentially, this creates the ability for the TFLN to handle much higher optical powers down in that visible regime. I think I'll end that there. If you'd like more information, let me know. But safe to say there is things we can do to avoid the photorefractive effect.
Sean, we had another question on that topic. I'll just kind of cherry pick these.
Yeah, sure.
Continuity. They asked, what is the highest laser power ballpark estimate that can be used in TFLN photonics before damaging the optical components?
Yeah. Okay. Good question. So an estimate, okay, the highest laser power is very dependent on the wavelength. At 1550, we might see up to 2 watts through a waveguide. At 500 nanometers, maybe we would see 50 milliwatts. But it's very dependent on the power density in that waveguide. Imagine you have 2 watts spread across a 10 centimeter wide waveguide. That's much different than 2 watts spread across a 1 micron wide waveguide. But generally, I would say in industry, people have gone up to about 1 watt at 1550, and then at the lower wavelengths, it's very dependent on what you've done to your TFLN in terms of doping and avoidance of that photorefractive effect.
All right, let's do one more here, and then we can turn it over to any live questions. I see there's more questions in the chat too, so we'll capture those and get to as many as we can. Since these wafers are made by bonding, what's the maximum temperature they can tolerate?
Yeah, these are great questions. Um, So this is actually a really interesting one because I would say the emergence of TFLN in industry has really come down to our perfection of the molecular bonding process of that TFLN film. If you look at papers and reports and literature from the perhaps 2010 to 2016 era, you'll see that TFLN films were bonded on top of an SU8 photoresist or a UV15. These are polymers, of course, so they have very low temperature tolerance and high loss. But then people figured out how to bond the TFLN directly to an SiO2 layer, or the amorphous version of quartz. So with that, all of these materials have a very high temperature handling capability in themselves. The problem comes down to the coefficient of thermal expansion between them when you heat them up too much, for lack of a better term. I would say in terms of damage to your PIC, if we're talking just a TFLN waveguide, probably you could get up into the 600C regime, which is more than anyone generally will want to heat their chips up.
Thanks, Sean. We'll just pause there with the chat questions and see if anybody would like to come off mute and ask a question live. All right, hearing none, we'll go back to some of the ones from the chat. Sean, you touched on this a little bit, but I'll ask it just for completeness. Can TFLN be integrated on the same PIC with photodiodes to build a transceiver on a single chip, for example?
Yeah, definitely. If we only have TFLN modulators on a PIC with nothing else, it would be a great PIC for some things, but maybe not for things that people really want to do with it. So foundries have established ways to integrate active devices, lasers, photodiodes onto a TFLN PIC. That's certainly not to say we're making them out of TFLN, but we can do things like etch a trench in the TFLN to drop in or flip chip some of these devices. And in some cases, foundries now are starting to bring TFLN into a silicon photonic process. Or say, let's just put a TFLN layer in an existing process with photodiodes and VOAs and amplifiers and things like that, such that we can all have it. We have the best of both worlds. And again, if you're interested in that, please reach out. It's something we have some experience with here at Spark. And I'd love to talk about it.
Great. Sean, we'll give you one more, then we'll switch over to a couple questions for Matt. I want to keep him on his toes too. On slide 14, Sean, what's the typical bandwidth for thermal optic modulation?
Yeah, that's a great question. Thermal optic modulators are slower than an electro-optic modulator, of course, but in some cases more stable. So the highest bandwidth I would count on if you're designing a PIC with a thermal optic device is in the 1 kilohertz range. In a lot of cases, they go higher than that, but to be sure you're getting what you want, I think about 1 kilohertz is what you can expect. Of course, that's limited by the heating and cooling time, generally the cooling time, really, of these devices. So we'll do things like etch a big trench on each side of that, such that it's exposed to air, so it cools down faster. But 1 kilohertz or less is a safe bet.
Thanks, Sean. We had a question here that was part for you and part for Matt. So let's use this one to make the transition.
Sure.
First one is actually 3 questions for you, and then it goes over to Matt to ask about IPKISS's suitability for this. The question says, you mentioned very high-speed switches. The switching will no doubt be very fast. However, what's your take on these 3 problems? 1, routing RF lines for dense switch meshes. Switching speed might become limited by routing lines cut off. 2, can crosstalk be avoided or minimized in dense switched meshes? And 3, how to keep the switch output stable in the constant state in between switches?
Yeah, good questions. So I did see that question, and I wanted to touch on that a bit in my packaging talk, but that's why I highlighted flip chip bonding or bump bonding for these sorts of RF connections. The goal there would be to avoid long, high-frequency electrical lines right next to each other, essentially acting as an antenna, which we don't want to do on our PIC. So there are certainly ways to avoid interaction between RF lines and loss in RF lines on a PIC. In some other cases, if we're not able to do flip chip bonding or bump pads, foundries will offer many different metal layers on these PICs. So we could say, let's make, at maybe the most basic option, a very thick metal layer that has low loss. Or let's route nearby electrical lines on different metal layers far away from each other so they don't interact. So there are things we can do to minimize crosstalk, and with dense integration, that's always the goal. How to keep the switch output stable in the constant state. Generally with TFLN, we do see some drift on the electro-optic side of things. It can be on the order of minutes or hours. This is called charge relaxation. And this is why we integrate thermo-optic electrodes or bias control onto these devices. So a thermo-optic switch is very stable, but slow. So we can integrate a thermo-optic switch to keep the bias state of these TFLN modulators constant, and then use high-speed switching with the TFLN electrodes.
Great. Thank you. Then Matt, over to you. The second part of that for you was, how well is IPKISS suited for including these RF aspects?
Thanks, Kevin. I think Sean did a great job actually of covering it. A lot of it comes down to the design you use. Obviously, there's no issue with using a GSG trace in IPKISS or other RF routing configurations, but really the performance gains that you'll look for are down to which layers you choose to and what areas of the chip you reserve for routing and how far apart you keep things. Obviously, that's all very easy to change. But I would say inherently, IPKISS isn't going to do that for you, sadly. We're not there yet. Maybe give us a year or two. But you can build in models into IPKISS that are aware of things like this, or the best case is to design around it, as Sean was saying.
Matt, we had another question for you. Is there a reason to have unequal opening for the multi-level eye diagram? I think on last or second to last slide you showed. Is it related to the material of the TFLN or the driving voltages?
I think that's just due to the driving voltages. That's the different levels that are chosen. I'm not an expert myself, so if anyone in the chat is, please correct me. I believe you would either choose balance levels where it's sort of they're equally spaced, or in the example I showed, they had the lower levels are closer together because it's easier to distinguish 1 from 2 volts as it is from 4 from 5 volts. So I think it's just a practical thing.
And then Matt, another question for you. I'll phrase this a little bit more broadly. How would one go about accessing the layout-based simulation kit?
Sure. So all the simulation tools I showed are built into IPKISS. It's all part of the same package. IPKISS is not free to use forever, but you can get an evaluation license from us for a month. If you're interested in trying it out, let us know, and we'd be happy to send one out or join one of the courses I showed. We also provide evaluation license with them. We also have a range of options for academics, research, and commercial users. So yeah, please get in touch if you're interested. We'd love to talk.
Great. Thanks, Matt. Sean, back to you. We had a question. What metallizations are possible for contact pads? Is gold the only one possible?
Oh yeah, great question. Gold is certainly not the only one possible. Gold is a nice material because it doesn't oxidize, but in some cases it's difficult to integrate into an existing silicon photonic process. So we very commonly see aluminum and copper integrated onto these chips as well. Generally, this is foundry dependent, so a foundry will have its metal that it uses. I assume they would be reluctant to switch to a different one, but if you have some requirement, there may be options for you.
Some questions on materials here. While TFLN is gaining a lot of traction in the industry now, do you think other materials such as barium titanate, BTO, will overtake it in the future?
Yeah, I mean, I certainly can't tell you that TFLN is the end-all material. I'm sure we'll eventually find something better. But for now, TFLN is a kind of a breakthrough material that is now finding its roots in industry. People are figuring out how to make it. It's not overtly expensive that it creates issues there. Barium titanate is a great material too. Its electro-optic constant is extremely high, but it's more difficult to fabricate. So I can't speak to how many years or if ever it will overtake TFLN, or if maybe that will be some other material. But for now, I think it's a safe bet that TFLN will be prevalent for at least another few years, I hope.
Good. And then can you comment on trade-offs between using an etched TFLN approach versus TFLN bonded to silicon or silicon nitride wafers?
Yeah, so when you design a TFLN system, there's different parameters that might be important to you, different figures of merit. Generally, with an etched TFLN system, your figure of merit would be high-speed operation, maybe high power handling, and ease of process if you can etch the TFLN. The disadvantages can be, in some cases, I say can be because not always, that it's more difficult to make things like edge couplers, of course, photodiodes, lasers, things like that. So if you can bond it to a silicon wafer, you have much lower power handling capability because of silicon, but you have more dense integration. You could have photodiodes, you could have VOAs, and all things like that. This would be a silicon waveguide on top of a TFLN slab, such that some of the optical mode is in the silicon. Unfortunately, silicon's a pretty high effective index. You're around 3.47, 3.5 there, compared to TFLN's 2.15 in the extraordinary axis. So you're pulling a lot of your optical field out of the TFLN, and your modulators are less efficient. Silicon nitride, on the other hand, is a great material and is actually very commonly integrated on top of TFLN, even in some foundries that can still etch the TFLN. Silicon nitride is very easy to etch, so it generally provides waveguides with low scattering losses. And silicon nitride is also transparent, I believe from about 500 to, or perhaps less, 300 to 5,000 nanometers as well. So it can be a great material to incorporate on your TFLN chip, and it's very widely used in things like sensors and passive applications down in that range. I think that covers it.
Thanks, Sean. What is the normal fiber to chip coupling efficiency for TFLN waveguides to lens fiber and cleave fiber?
Yes, great question. I would say in industry, the presentable numbers are probably about -1.5 dB to probably -5 dB. In a lot of cases, if you can integrate a silicon nitride waveguide at your edge coupler, it's a lot easier to match the mode field of the fiber. If you can use a lens fiber, that's awesome, although sometimes it's difficult to package. But if you can't do those things, we usually get into that 5 or 6 dB of optical loss range. I will say that's rare. If I could estimate the average, probably around 2.5 to 3 dB per edge coupler.
And I know you spent a lot of time working on that kind of thing with folks. What's the maximum bandwidth achievable with electro-optic modulators, and what are we currently achieving? You mentioned 1 terahertz as the upper end.
Yeah, great question too. So TFLN does not use the plasma dispersion effect of something like silicon. So you're not moving charge around, which takes less power and you can do it faster. You're essentially moving the electron cloud of the atoms and molecules in the TFLN. So it can be done much faster. So the limitation that you encounter is your electrode design. People have used standard CPWs or coplanar waveguides with 2 grounds and then a signal in the center. In this case, you'd be capacitance limited, loss limited, and velocity mismatch limited, where your optical field doesn't travel at the same speed as your electrical field. To fix this, a lot of people lately have been designing segmented electrodes, or what they call capacitively loaded electrodes, to slow down the optical field and reduce current density in the interaction region, so you lower your electrical loss. But I noted segmented, and you can think of when you get high enough in your RF frequency, you have now kind of designed a Bragg grading into your electrode. So you'll have very little RF transmission through that electrode if you're just reflecting it all. So the limitation is then electrode design. If you want to get up into 1 terahertz, which has been shown in literature, or 500 gigahertz even, you can do it. You're going to have higher voltage operation because your electrode will be so short. And from an industrial point of view, you can't drive a 500 gigahertz or a terahertz with a CPW or an electrical waveguide. So you would need an actual waveguide, or a metal rectangle that your wave goes through to feed this device. There's no coaxial cable that will support that sort of bandwidth.
Good. Thank you, Sean. Folks, we're at the 1 hour mark. I want to be respectful of your time. I know there are a few questions we didn't get to. Ask those folks to please reach out if you'd like, and we would be happy to continue the conversation offline. My thanks to Matt from Luceda Photonics and to Sean from Spark Photonics for the very insightful presentations. Thanks to everybody for joining and for your great questions. It was really exciting to engage with you all, and we look forward to seeing you at another event again soon.
Thanks, Kevin.
Thanks, everyone.
Bye, everybody.